Howdy everyone, welcome to the Country Chemist. Today we are going to be talking about kinematics, namely one-dimensional kinematics. In another video I will cover two-dimensional kinematics. So everything I'm doing here is either only in the vertical direction or only in the horizontal direction. However, my explanation in the beginning, when I talk about the types of equations, will remain the same for both. So these are the four kinematic equations that you see come up again and again and again in kinematics. In these equations, some of these variables might change. You might see different formats. For example, instead of seeing a d, you might see an s, or you might see an x in its place for any of the d's in here. There's one change that you see come up quite often in physics. Another change is that instead of seeing a 0 for initial, you might see a 1, or you might see an I. And then for final, you might see a 2, you could see an F, and you could see a 1 if this is a 0. The point is to differentiate between what is final and what is initial. It doesn't matter as long as you keep this order consistent. A lot of people like to point that out when you're learning math, that it doesn't matter what you call a variable as long as you know what it is. For example, instead of using A for acceleration, I could use the letter W and call W acceleration. As long as I plug the right value into there, it does not matter. Okay, so let's talk about these variables. D is for distance. If you have s or x, it also means distance. A is the acceleration, t is time, and v is velocity. And like I mentioned earlier, v naught, v0, or vi means initial velocity, while the other one will be final velocity. You'll also see different variations on how these are written. For example, I wrote this delta d, meaning a change in d, which means I could write this as d final minus d initial equals 1/2 at squared plus v naught t. But I've also seen this written out where instead of writing it this way, they'll just put it at the end, which means write all this down and then, of course, because you have to change the sign, plus your initial d. So there are lots of different ways of writing this, and whatever book or formula sheet you're using might have it in a different format. That is okay. Since most people like to keep their initial distance being 0 and their initial time being 0, by the way, delta t is time final minus time initial, but in most cases, initial time is 0 and initial distance is 0. So a lot of people just rewrite these formulas as d equals 1/2 at squared plus v naught t. And you'll see that for a lot of these. Like this one will be 2ad. This one would be at. And this one would also just be a t, and this would just be a d. There's a lot of different formats, and there's reasons why you might want to use one format over another. Though this is the simplest, and I usually will use this. However, if I have a need to put in an initial distance, I will do it. Usually you don't have to put in anything for time, but for distance that comes up a lot. Okay, so when you're solving these kinematic equations, there's 4 important steps to consider. First, always draw a picture. A picture shows that you can put the word problem into view. If you can't see it, it's going to be a lot harder to understand. Once you have a picture drawn, determine what your variables. In a kinematic equation, you always have the same variables. You have a final velocity, you have initial velocity, you have acceleration, a distance, and a time. In special circumstances, you'll also have an initial distance, in which case you'll have to define this as your final distance, and you could have an initial time if you're not starting at 0, though that is pretty uncommon. But until I have a need to insert an initial distance, I will remove it and not make it a part of this. Now notice in our kinematic equations, every one of these has 4 variables in it, but here I have 5. Let's check that out. Here you have d, a, t, v naught. There's 4 variables. Here we have v final, v initial, a and d. Here we have v final, v initial, a and t, and d, v initial, v final, and t. Every one of these cases we have 4 variables, but here we have 5. Additionally, every one of these has v naught in it as one of the variables. And I'll bring up why that's important in just a sec. Okay, so let's assume you're given a question, and they give you these 3 variables. If they give you 3 variables, because all of these have 4, you can solve for the last one easily. Let's say they give you velocity final, velocity initial, acceleration. They say let's solve for time. Then find the equation that does not have distance in it, which is this equation here. This equation does not have distance in it. So this is the equation you use to solve for time. If you use one of these other equations, since you don't have time, you would be forced to use this equation. And then this would solve for distance, and you still didn't get your answer. So then you have to do 2 steps to get your answer. And that is not an effective use of your time. So always find the variable that you don't have, that you don't need, and then find the equation that doesn't have that. Okay, so let's say we have v final, acceleration, and distance. Notice you always have to have 3 of these. I'm going to keep pointing that out. You have to have 3 of these. If these are the 3 given and they ask for time, this is where we start to have problems because every equation has v naught in it. Which means now we must make an exception. Instead of what I said a moment ago, where I said find the variable you don't have that you don't need, if v initial is the variable that you don't have and don't need, you have to solve for it anyways. This is the only exception because every equation has it. So find the equation that doesn't have time in it, which is this one, solve for this variable, so then you have something to put in there, and then use any equation with time in it to solve for time. Let's do one more example. If we are given these 3 and we say solve for final velocity, then we're giving 3 different terms, and we are also given v initial, which is important, which means now I follow that rule I mentioned originally. I don't need time, so we'll find the equation without time in it, which is this equation. So I use this equation to figure out what the final velocity is. Okay. So recap the rules. 1, draw a picture. 2, determine the variables, as in write this out, write down what they equal, put them all in the right terms. So if this is meters per second, this must also be meters per second. This has to be meters per second squared. This has to be meters, and this has to be seconds. Notice all the units match. If this is yards per second, then this is yards per second squared, this is yards. If this is centimeters, then the centimeters per second squared, and centimeters. Make sure all the units match when you do this. So write down your variables. Write down what you know from the equation. If it's something falling, acceleration is always negative 9.8. So write down what you know from the problem. Then go into here, find the equation, step number 3, find the equation, plug things in, and step 4, solve, and you will have your answer every time. So here are 2 examples that I found on Google. By the way, if you need any worksheets for these, you can easily run a Google search for kinematic worksheets and find several example problems. This first question says Georgia is jogging with a velocity of 4 meters per second when she accelerates at 2 meters per second squared for 3 seconds. How fast is Georgia running now? Okay, so always start with a picture. Although this one you might argue and say you don't necessarily need one, but for sure when you're first getting started with this, draw a picture so you understand what is happening. You have some initial spot. You're moving forward at 4 meters per second. And you're accelerating at 2 meters per second squared for 3 seconds. Now, all this is in the same direction. That means everything is positive. Okay, so let's go ahead and fill this out then. Velocity final, velocity initial, acceleration, distance, and time. Let's go ahead and plug this in. Okay. So we don't know what the final velocity is, but that is what we are solving for. It's asking how fast is she going now. So this will be what we're looking for. Velocity initial is 4 meters per second. Acceleration is 2 meters per second squared. Distance we do not know. And the time is 3 seconds. Okay, so we're given 3 variables. So now we can solve for what we're missing. We do not need distance. We'll find the equation doesn't have distance in it, and that is this equation right here. I always advise manipulating your variables before you plug in numbers, and this one actually works out well because we're solving for final velocity and it's already by itself. So let's go ahead and plug that in. Final velocity equals initial velocity, which is 4 meters per second, plus the acceleration, which is 2 meters per second squared, times the time, which is 3 seconds. Now note that I did not write units in here. Although you should, because all these are written in the right terms, I'm not going to do that. This is in meters per second, this is meters per second squared, and this is seconds. So seconds cancel out, and this is meters per second plus meters per second, so my answer is also in meters per second. Notice how that is consistent with what I wrote here. Okay, so let's go ahead and do this. 2 times 3 is 6. 6 plus 4 is 10. So the final velocity is 10 meters per second. That is our answer to the first problem here. Okay, let's take a look at the second one. In the second problem, it says in a football game, a running back is at the 10-yard line and running up the field towards the 50-yard line. It runs for 3 seconds at 8 yards per second. What is his current position in yards? Okay, this doesn't matter. This just tells me he's moving. So this is where the drawing comes in. You're at the 10-yard line. You're moving towards the 50-yard line. So I don't actually care that's a 50-yard line. Just know I'm moving towards it. Which just kind of gives me a bearing. That's about it. You're running for, let's see, 3 seconds. And you're going 8 yards per second. Okay, cool. Let's go ahead and write down what we know. We have our final velocity, initial velocity, acceleration, distance, time. And for this particular one, it gives me an initial distance of 10. So let's go ahead and write in that extra variable. So that's distance final. Let's make that look just a little bit neater. And we have distance initial. Okay, cool. So what's great about this problem is that acceleration is 0. So final velocity and initial velocity actually equal each other. And we have 8 yards per second here. So first of all, this says yards, which means distance has to be in yards. And if we had an acceleration, it'd be yards per second squared. Also, anytime that acceleration is 0, the 3 variable rule no longer counts. Because if you look at the equations here, a lot of them end up canceling out. You put a in here as 0, v final equals v initial. It doesn't tell us anything new that we don't know. I do that same thing here. This cancels out. V final equals V initial. It doesn't tell me anything I don't know. So the 3 variable rule does not apply with these 3 variables because this doesn't tell me anything. Let's continue on. We have 3 seconds and we have initial distance of 10. Okay, cool. So there's a very simple equation that I can just throw out and use. And I would say that this is another one that you should have memorized, D equals VT. But if you don't have this memorized for some reason, that is okay. Check out the very first kinematic equation I have written. Distance equals, all this cancels out, V naught times T. So let's go ahead and write that down. So change in distance. Change in distance. So this means D final. I'm going to go ahead and move D initial to the other side. So this equals V naught T plus our initial distance. Okay, cool. So let's go ahead and plug everything in. Our initial is 10. Our velocity is 8 yards per second. Let's go ahead and write our units here, so I'm just consistent. 8 yards per second, and we're going 3 seconds. So this is 24 plus 10 equals 34. So he is at the 34-yard position on the field. I almost caught myself, almost said yard line, but the yard lines are in multiples of 5. Okay, so 34 yards in on the field. So far, these are not too bad. Same thing, each case, I wrote some kind of picture to make sure I have the right bearing, so I know what I'm looking at. I write out my variables, and then I find an equation that works. Once I do that, I plug in, and I get the answer. So far, so good. Now we're going to step things up and make it just a little bit harder. In this diagram, not all the numbers given are going to be useful and not everything is given. So we need to actually think a little bit, and this is where our picture really does come in. Questions like this are a staple for kinematic classes. You will see this come up again and again and again, but usually with a horizontal component as well. So I will take this question We'll work it through, and I'll give you a very quick example as if it did have two components to it, an x and a y component, just so you get a little bit familiar with it, even though that's not in the scope of what I want to cover. Okay, so let's go ahead and draw a picture. It says Isaac throws an apple straight up in the positive direction from 1 meter above the ground. So if the ground is here, it starts throwing from here, it goes straight up. I'm going to do it as an arc, even though it's going straight up and back down. And then it comes all the way down and hits the ground. This is 1 meter, and this total height here is 35 meters. Neglecting air resistance, as we always do in these classes, what is the ball's velocity when it hits the ground? Okay, this is all that's given. And in fact, to make this even worse, this isn't even important for our question. So we're only given one number. So how do we solve this? Let's go ahead and write down what we know. Velocity final, velocity initial, acceleration, distance, and time. Okay, so what do we have? What are we looking for? Okay, in fact, I can go one step further, and let's do a final distance and initial distance. And I'll explain why I'm doing that in just a sec, because I think that's going to be pretty important to how this problem solves out. Okay, we are solving for the final velocity. Cool. What is the initial velocity? We don't know what the initial velocity is here. However, if I start the ball here at the top, the initial y velocity is 0. So that will give me a value if I start up here, which is why I said that 1 meter is not important. In which case, acceleration is going downwards. It's gravity. It's negative 9.8. Okay, so far so good. And now let's talk about distance. If I say the starting point, now this is where you can mess with this a little bit. I can say the starting point is at 35 and the ground is at 0, or I can say I start at 0 and I go to negative 35. This is up to you. You'll get the same answer either way. If I say the top is 0, then I can say that the ground is negative 35. Or I can say that the ground, the final distance is 0 and the top is positive 35. The math will work out the same way. But I'm going to set it up this way. Now we have our three variables again. Notice that delta D is what I'm considering a variable. So we have 1 here, 2 here, and then both of these together make up 3. So we have all three of our variables. So what are we looking for? We're looking for the ball's velocity when it hits the ground. So I don't care about time. The equation without time is this one here. So let's go ahead and use that equation. Velocity final squared equals velocity initial squared plus 2a, and I'm using delta D, so initial minus final. Let's write it out first, and I'll plug everything in. Okay, we're solving for final velocity. Fantastic. So final velocity equals the square root. Okay, so let's talk about this. This is 0. I'm not going to write it down. That's 0. Cool. Okay. Now we have 2 times acceleration, which is negative 9.8. And then for distance, it's final minus initial. So here I get negative 35. Now, what happens if I had these flipped? What if I called this 0 and this positive 35? Then final minus initial is still negative 35. So you see, it doesn't matter how I wrote it as long as it was consistent with my diagram. The math works out the same. Okay, cool. And what else do I know that's missing from this graph? A square can either come from a positive or a negative. Is this final velocity supposed to be positive or negative? Since I'm going in the downward direction, it should be negative. So I'm going to write a negative in front. My answer will be negative. Okay, so let's go ahead and type all of this in. Okay, as I type this in, the answer that I get, we have the square root of 2 times 9.8 times 35. And what this gives me is negative 26.2 meters per second. Okay, cool. So this is our final velocity, and this is the answer to our problem. Now, as I said, I was going to add something to this. I was going to ask one more question, because we need to know how to solve these when they do come up. But I'm going to be brief on this, because I want to cover this through another video. What if there was a horizontal component? What if this ball was also moving forward at, let's say, 3 meters per second? Not only was it being thrown up, but also was going 3 meters per second forward. So let's go ahead and do that. This is our y component, so this is our x component. We can write down all these, but actually I'm just going to write down all of them. I'll explain to you the shortcuts that you could use. Okay. Acceleration is 0. We don't care about air resistance. So as far as I'm concerned, velocity final and velocity initial are the same. So I really just have to write down these 3 variables. Our initial velocity is 3 meters per second. Cool. So with these 3 variables, the equation that we use is distance equals velocity times time. I mentioned this in a previous one. It's from this first equation. Just cancel out this term and you have it. But you have used this equation before. If I asked you if you're going 60 miles an hour in 2 hours, how far do you travel? You already know to multiply those two. This is something you've been doing before. Okay. So let's ask, how far forward does the ball move before it hits the ground? Okay, this time here and this time here are the same number because it's the same ball. So this variable is linked between the 2 columns. Okay, so we need to solve for time. So we find an equation that has time in it. And since I have final velocity, I can actually pick any equation with time in it. And let's go ahead and let's choose this one. Final velocity equals initial velocity plus at squared, or at, yeah. Final velocity equals v naught plus at. Okay. So the initial velocity is 0, so I don't have to worry about it. So final velocity equals a delta t. I'm just going to write at. Okay, cool. So if I'm solving for t, this means that t equals v over a. Okay, so this is negative 26.2, and my acceleration is negative 9.8. Fantastic. So now I can plug this in to solve for my time, in which case 26.2 divided by 9.8 equals 2.67. seconds. So 2.67 is my time period. Cool, and that has to be the same time period here because this is the same object. Fantastic. Now I can plug these 2 in, multiply them, and get my distance. So time gets plugged in for t, and this gets plugged in for v. So distance equals these 2 multiplied together, which is 8.02. 8.02 meters would be my distance in the forward direction. This will come up a lot in kinematic equations. You will start out by learning one dimension, like I have had in the last board and this board, and then they'll start throwing in the second dimension here. Like if it's moving outwards. If it's not just going up, it's also going forwards. Where will it hit the ground? This question will come up again and again and again. So you need to know how to relate these 2 together. Okay, but since I don't want to talk too much about 2D kinematics, let's call that good for this problem. The main focus was on this here. Okay. Okay, let's go ahead and cover one more problem, as I think this is one of the hardest that you will see in one-dimensional kinematics. There is one variation of this, which is even slightly harder, but in questions like that, they just give you acceleration. You do the same concept that I covered in this one. Okay. Two kittens on opposite sides of the field. They're 250 meters apart. Kitten A runs with constant speed towards kitten B, and kitten B runs with constant speed towards kitten A. How much time elapsed for the two kittens to collide? Okay, let's do our picture. So they are 250 meters apart. We have kitten A, and we have kitten B. Kitten A is moving in this direction at 25 meters per second. And kitten B is moving in this direction at negative 12 meters per second. I'm calling it negative because I'm going to call this the positive direction. Okay, let's go one step further. We need to talk about distance. Distance is something we are missing from this. We might have 250. That's the total distance. If I plug in 250 in either of these equations, I don't figure out where they meet. I figure it out when they get to the other side, which is not what I'm looking for. So let's say the distance traveled by A to get to here is x. So the distance that B covers to get to here, and this isn't directly in the middle, I just drew it here, is negative 250 minus x. Why is it negative? X is moving forward, and then 250 minus x covers this distance here, but B is moving this way, so it's a negative distance that is covered. Okay, let's go ahead and write down our variables. Velocity final, velocity initial, acceleration, distance, time, velocity final, velocity initial, acceleration, distance, time. So one is for cat A, one is for cat B. Okay, so these are actually pretty straightforward because there's no acceleration. So just like I said in the previous page, I don't really care about these terms because this equals the final velocity because there is no acceleration. If there is acceleration, go ahead and plug it in. You'll follow the same steps. Okay, so let's see. Our distance here is x, and our distance here is negative 250 minus x. Okay, what else do I have? The initial velocity here is 25 meters per second, and the initial velocity here is negative 12 meters per second. Cool. Now what I have is a very common thing that you see in algebra. I have two unknowns. I don't know what x is, and I don't know what t is. So I need to have two equations in order to solve for that. So let's go ahead and write two equations. And this is where the overlap comes if we do have an acceleration. Okay, so I need to find an equation that has these three variables. Of course, in this one, we already know it's v. We already know it's d equals vt. But if there was an acceleration, just find the equation that has that. If you find an equation that has acceleration, you still are going to have two variables. For example, if it was this one, let's say you don't know what distance is and you don't know what time is. So you'd likely know what acceleration is. It really depends on how it's worded. But let's say you don't know what these two are. Well, all the other variables are given, so there's still only two unknowns. As long as there's only two unknowns, you can do this for both equations and then substitute them. Okay, let's go ahead and fill this out then. So distance is x, velocity is 25, and time is just t. And since this is one system, time is the same for both. Let's talk about this one. Negative 250 minus x equals velocity of negative 12 times t. Now I have to do a substitution. I have to plug one equation into the other to cancel out a variable. Since I care about t, I don't care about x, I care about t, let's plug in 25t into x so x disappears. So I get negative 250 minus 25t equals negative 12t. Cool. Now I can cancel out these negatives. So 250 minus 25t equals 12t. So 250 equals 37t. So t equals 250 divided by 37. And let's pull out a calculator. 250 divided by 37 equals 6. Let's go ahead and write this down. 6.76 seconds. This is the time required for the two kittens to reach each other. And as I said earlier, if this was a question that was given with an acceleration in it, then just pick an equation with acceleration in it and then set the two equations into each other like I did with the substitution method, so time is the only variable left. And you will still get an answer. So there are harder variations of this question, but as far as one-dimensional kinematic goes, this is as hard as it gets. And if you can do problems like this, you are set. In a later video, I will cover two-dimensional kinematics so that you can start becoming familiar with that as well. I covered one question earlier, and I will be covering more later. I know that physics can be seen as one of the harder classes that people take at high school and in college, and I want to do whatever I can to make it easier for you. Thank you for your time. If you like videos like this and want to stay up to date, please hit subscribe so you can see new videos as they are posted. Thank you very much, and stay tuned.